Hello everyone. So time to do day 6 and 7. I hope. I didn't do them yesterday and the other day, but today and the other day. And let's start with day 6. So Guard Gallivant. The historian used their fancy device again, this time to whisk you all away to the North Pole in 1518. Okay, why is it 1518? It is the same year of another day of Advent of Code. Okay, so we are still getting references from the other years. In 1518, it turns out that having direct access to history is very convenient for a group of historians. You have to be careful of time paradoxes, so it will be important to avoid anyone from that year. I mean, you do not have to touch people to avoid time paradoxes. That's how it works. And a single guard is patrolling this part of the lab. Maybe you can work out where the guard will go ahead of time. Okay, so here we have a map. The map shows the current position of the guard with this symbol to indicate the direction of the guard. Okay, any obstruction are shown as a dash, as a hash. Lab guards in 1518 follow a very strict protocol which involves following these steps. If there's something directly in front of you, turn right 90 degrees. Otherwise, take a step forward. Okay. Following the above protocol, the guard moves up several times until she reaches an obstacle. Okay, so we are following the guard. Here it goes to the right, then it goes down, then it goes to the... Okay, it continues, and at the end she leaves the mapped area. By predicting the guard route, you can determine which specific positions there will be in his path. So, including the starting position, we want to count all the positions the guard will be in. Okay, so here we have to have 41 distinct positions. So, predict the path. How many positions will the guard visit before leaving the mapped area? Okay. So, we are gonna work with matrices today. Scaffold day 6. Now we have day 6 here. The example which you have to fill in. Let's start with the example. I don't even want to watch the input right now. So the input is this first matrix here. And let's go here and copy that. Okay. So I don't want to waste time writing the grid again, so I'll just copy it from yesterday's code. It was, no, not yesterday's code, but the 4th day. There was a grid somewhere else. Okay, yeah. This one. So let's copy some of the code for the grid. Right here, I will put it in a library, maybe outside the streaming. So here we have a string. We collect everything. We can get something. Now I will try to refactor this code. So we don't need the Christmas, the Xmas stuff and the pattern matching. We just need to go on the grid and get something. Now the get can become an option. I wanted to improve that yesterday, but didn't do that. So if self is inside yx, then if it's not inside, we return none. Otherwise, we return some of this. Nice. Now, another thing we need to do is find the first position of the guard, or maybe we can just put it there by hand. But let's start by defining this guard. So the guard have a position. So struct guard has a position. So y. Let's do it with integer because the guard can be outside the matrix. And next, it has a direction, which we don't know yet, and nothing else. So let's define the direction. We can be north. Let's go rotating clockwise. So north, east, south, or west. Okay, she has a direction. The nice thing about implementing the guard like this is that we can already implement the guard the guard algorithm. I say algorithm. So the guard can have, we can pick the next position and change the position of the guard. So the first thing we can do is we can pick the next position of the guard based on the grid. So we give it the grid, which is a reference to grid. Then we get a new, I mean, we can just change this guard into position, maybe. This is a position in the map. So we return a new position. And and then we can also, oh wait. No, actually, this will just return a pair of numbers, because we are just picking the next position based on the current direction, so we don't need a new direction. So how can we do that? And we also don't need the grid, I think. Okay, so we can match the current itself. So we get the current direction and we match the 4 arms. If we are north, then our next position will be self y plus 1, because we are going north, and self x is the same. If we go east, then self y is the same, self x is plus 1. If we are going south, then we have, oh, actually, yeah, self y plus 1. I must correct myself. The y is on the, is going down, and the self x is the same. Otherwise, self y is the same, self x goes to the left, so minus 1. The other thing we can do is, I'm just writing the specification of the problem here. We can advance, so we can do a step of the guard. So here we have mutable reference to self, and we have the grid because we need to check for obstacles. So we have a grid. Let me check this. So I need to pick the next position. So let the next position be the next position. If now, okay, so if we have an obstacle, so if the next position is an obstacle, now I would like to do that like this. So it is an obstacle, the next position. If this, then I need to turn by 90 degrees, and then we can, otherwise, we can just advance, so self advance. Now let's write these 3 methods. These 3 methods. So the first are the turn. It gets a mutable position. Oh, let's call it guard, because guard is changing positions right away. So I need a new name. So let's turn by 90 degrees. This does that match of our direction. We just need to change the direction. So self direction, and self direction will become this new direction. So let's write that. If we are going north, then we go east. If we are going east, we go south. If we are going south, we go west. If we're going to go west, we go north. We are turning 90 degrees to the right. And the advance method, again, gets self, returns nothing, and we just go to the next position. So let the next position is pick next, and self y is the first number, self x is the second number. That's what we need to do. Now the last one is obstacle. So function is obstacle. We get the grid and we need a position. It returns Boolean. Now how can we do that? We can get the cell in that position, and if we have a match, if we are if we are not inside the matrix, then it's not an obstacle, it's okay. Otherwise it is an obstacle if we have a char which is the hash symbol, so this one. Okay, now okay, we need the next we can get a pair here maybe, so we need I might refactor this later. So this is position equals 0 equals 1. Does it work? Okay, this is working, and we can try to see all the positions the guard is taking. Now for the position I want to maybe write a getter. I don't like this, but we can just get that later. Or we can also transform this into an enum. So this is a coordinate. This is not an enum, it's a struct. Coordinate. It's an i32. i32. Does it work like this? Okay. So position is a coordinate, and self position 0. Yeah, I don't like this. Should be a struct actually. Yeah. The y is an i32, and the x is an i32. Maybe we can use that for the entire. This is a coordinate, so position y and self position x. Okay, let's put the position inside here. No. Here. Position x, position x, position y. Same thing, the big next return position and coordinate. So coordinate, oh yeah, we need to refactor this, so let's do it. Coordinate with a y, and let's close this. We need to give it an x, maybe. X, x, x. Can we do it like this? Okay, it works. The is obstacle can get a coordinate. The get can have a coordinate. Coordinate. A coordinate. So we can refactor everything. And again, chord y, chord x. The get here by passing the position. Okay, still working. Here everything works, and same thing here. Self position is equal to. We can make it easier. We can delete these lines. And this is perfect. Okay. This is the code for the guard, the coordinate, the directions, and the grid. So let's start with part 1. Part 1 requires us to count the number of positions visited, which is 41 in our case. Let's write this number and check that this works. So we start by having an initial position of the guard. So the guard has a position which I don't know. Let's start like this and we will continue later. And then we have a direction which is for sure north, because it says that in the problem. And let's see also in the example we have it facing north. In the input, let's see the input. Okay, it's quite bigger. Let's search for this character. Maybe yes. So we are lucky, still facing north, so we don't have to care about parsing the direction. Now, how can we find the position of the guard? We can have the initial position by looking inside the matrix. So grid. We need to create the grid. So let grid equals grid new from the input. Now, how can we do that? We can maybe write a find method to find a single card, the first character. So like find first, and we pass this here. Like this, and it will return an option. Let's write this method so we don't have it. Let's generate it. Now, how to do that? We need an option of a coordinate. So let's write it in the wrong way. For y in 0 self grid self height, for self width if self get of coordinate ix is equal to the argument, then return sum of the coordinates. So let's write this again here. The coordinate is this, and we write the coordinate here. We return the coordinate, otherwise we return 1. Does this work? No, because we need an I32. What this is? No? How do you format the file? I always forget. Forgot completely. Okay. Control Alt F. I don't know. Now X is not yet, because this Y is an X. Okay. Doesn't like the coordinate because it's moved. Because we need to pass a reference. So the get can have a reference coordinate. Can have references. Yes. Here it gets reference. Again, here we can use this. Now, this coordinate is the initial coordinate we find here. Now, what can we do? We can cycle until the guard is inside. So, while the guard is inside the grid, and we have a is inside for this, which must take a coordinate. let's take a coordinate. If coordinate y, coordinate y, coordinate x, and coordinate x. So here we can pass the coordinate. If the guard is inside, so if the guard position is inside, while it is inside, we need to count the number of not of steps but of positions. So I like to do it with hashmap. So positions is hashmap of coordinates. No, not hashmap, hashset. It is hashset. Okay. We put the position, so also the first position inside. So positions insert guard position, and we need to make a step with the guard while it's inside, and then we return the number of positions. 32. The insert, we're not satisfied. Okay, so let's go to the coordinate and give it some predefined derivations to derive EQ, at least EQ, but also copy and clone. Just a single record. Should work now. No. So also need a hash. Okay. Let's give the coordinate a hash. Hope it works like this and we don't have to write anything. Cannot mutate immutable positions. Okay. Now it should compile. Let's test day 6. And it works. So let's solve day 6. Maybe this will work. Hope it does. It does work. Nice. Okay. And let's go to part 2. So while they begin working around the patrol route, you borrow their device and step outside the lab. Okay. You time travel to the last 3 months and record the nightly status of the lab's guard on the walls. Okay, returning after what seems like a few seconds, they explain that the guard patrol is too large. Okay. They are pretty sure that adding a new obstruction won't cause a time paradox, and they'd like to place the new obstruction in a way such that the guard will get stuck in a loop, making the rest of the lab safe to search. Okay, they would like to know all the position of such an obstruction. The new obstruction, so we need to place an obstruction inside the grid to have the guard go in a loop. 6 different positions. Okay, so we have, this is the output they want, I think. Okay, so this is nice. Okay, so we need to detect loops in the guard position. How can we do that? Okay, so we need to detect a loop. Let's start with that. We need to detect a loop in here, given the guard initial position. So initial and the grid. We need to see if there's a loop. That's how we're going to do it. Let's try again with this. So copy some of the code here, and we can try. I'm doing the opposite of before. So before I was writing the guard implementation and then using it. Now I'm trying to think how to solve the search, and then we will try to. So we can start by brute forcing through the grid, so we can try all positions in the grid, and maybe we will work out something. So given the initial position, I'd like to do something like we try every possible position in here. So the obstacle is in this coordinate, like can I do it like this? Does it work? No, I need to give names to stuff. X is X as item 2, and we can count it in this loop. So if what did I write here? If we have a detect loop, and we also need to pass the obstacle, which is a coordinate. We need to return a boolean. Okay. So if it detects a loop given the obstacle coordinate and the grid, then we increase the counter and we return the counter. Okay. Now we just need to write a detect loop, and we need to put the obstacle inside the grid. So maybe we can modify the grid before writing the loop detection algorithm, and then we can reset the grid later, or maybe we can just copy the grid over, even if it's a bit large. I mean, it's not that small. It's 130 by 130. It's a square. Not too big, but it's 10 kilobytes, I think, at least. So we could copy that, but I don't want to. So let's give it a mutable grid and modify it. We get a mutable grid. We write something. So I should start like grid put obstacle in a coordinate. So the obstacle coordinate. Then I'd like to do the stuff, and then we can remove the obstacle like this. Let's write these two methods. So first one, put obstacle, or we can just call it set instead of get. So if it's not inside, we return. Now here we don't return anything. This is called coordinate, and we also need to write something here. So the character, otherwise we do this. We get the coordinate, the coordinate here, and we write C. Right? This is coordinate, and here we need the mutable self, and we need to go here and we set at the coordinate obstacle, we set a obstacle, or we can just set the hash. Yes, and then we remove the obstacle by setting. Why it's not working here? Takes 2 arguments. Yes. Let's put back a dot. Now we shouldn't put the dot here. we should reset the grid as it was, because if we, yeah, we should just copy the grid over and do this. So we don't get a mutable grid, we get a reference, we clone the grid. Now, how do we clone a reference? Maybe clone. Maybe just clone. I hope it works. Then we set the, we get it as we copy it as mutable. We set the obstacle we want, and now we can try to return something. Now, trying to detect the loop. So first thing is, how do we detect a loop? A guard goes in a loop if she comes back to the same position in the same direction. So we could try to record all the position and direction, so all the guards, we are all the new guard position, which we called guards. So we need a hash set. It's a set of let's do it like this. So it's a coordinate and direction of the guard. While, so we either go outside, we create a guard. So let guard equals to a guard with the position equal to initial and the direction, which is north. It always starts from north. And while the guard is inside, because if it goes outside, then we're done. While the guard is inside the map and the guard position is not in our set of positions, so if positions was it contains, is it contains, I need to see. Do we have a contains? Yes, we have a contains. So if it contains what? It contains a reference of this thing. Okay. A reference to the guard position and the guard direction. While it does that, we advance. So guard step with the grid. If the guard is still inside, the if the guard is still inside the grid, it means we have a loop. Otherwise, it would have gone outside in a. I mean, I hope so. Now, why does this not work? I'm doing this. Wait. Okay, this initial doesn't like that because we have already another. What? No, initial. And contains exists for the struct, but its traits were not satisfied. So what doesn't have an AQ? Oh, coordinate direction doesn't have an. Okay. We can try to do something else. We can return a new guard. We can use the guard itself because it has a position and a coordinate, maybe? No. Doesn't, because direction doesn't have the equal. I thought that struct worked, so like you need AQ, maybe even, well, we don't need a clone, I hope. Doesn't like it. We need hash. Why doesn't even need hash? Could be already hashable. So this is our code. Oh, it doesn't like the direction because it is moved. It doesn't, okay. So it does have to implement again, clone and copy. So it's the same as the coordinate. Okay. This works. This doesn't because it's not mutable. Let's make it mutable. And the grid is just a copy. It's mutable. Why is it not mutable? Yeah, it needs to be. We need to set. Okay. We need to clone the grid. The reference grid. So the grid should implement clone. I hope this does work in our code. It does. Okay, so we return if it's inside. Now, let's try to run this algorithm. We need to find 6 spots. If I remember correctly, yes. We need 6 spots here. So we go with 6 and we hope for the best. Okay, it failed. It found 100. Must be something wrong here. Okay. So our code is not working correctly. Nice. Let's see. We need. Okay. Oh, we are not running the guard. But first we step. We also need to put the position inside. So we insert into the position a coordinate, which is guard position, guard direction, I think. And position must be mutable. Now it should work. Still failing. Still finding 100 thingies. Okay. And we need the. Oh, why? If it contains, then it continues. No, wait. While the guard is inside and I'm not coming back to the same position, if I come back to the same position, then I have a loop. Now it works, okay. Again, let's try to solve the 6. Okay, it's getting a while. I think that trying every possible position in the... let's see how much it takes. But I think that trying every possible position in this one is okay, but in the input one, which is 130 by 130 position, is not that smart. It's taking too much. I think we can at least skip the position of the already present obstacles, so we can try that. Here we can filter. Like, let me just add this. If it's not an obstacle, then if it's already an obstacle, I don't need to put a new one. So if it's not an obstacle, and I detect a loop. Now let me change this because it's too long. Maybe, let me test it again. Maybe we can solve it faster, but I don't think, because there are still too many positions, too many coordinates in here. Let me see while it goes. Let me see if it works first, and if we can, I mean, if it takes less than a minute, then we're okay. Otherwise, We can maybe check. Maybe we can, I don't know. We already have a first path that the guard is taking. So maybe we can just put the obstacle in one of the X positions here. So maybe we can use the result from part 1 to like make it faster. Oh, it returns something. So let's see if this is right, at least. It is right. So day 6 is done, but I think we can do it a little bit faster. So let's copy the part 1 and see. So we have a guard. Let's take the positions. So let's extract this code here. At least this one. And extract the code. And this is guard steps from a coordinate given a reference to a grid. I want to return a U32. So here will be some. No, I don't want the. I want the hash set of coordinates. So we can we return the positions actually. I want the positions. So I return the position. Here I have len. And here I just get the positions. Guard steps of initial grid. And I just cycle over the positions. So I do positions filter and I filter. So by definition, the positions in which the guard is are not obstacles. So if I can detect a loop from here, so if I have a position pause and I detect a loop and obstacle is the position, from the initial position we add an obstacle in the current position in which the guard is into the grid, and if it's a loop then we can count it as U32 and put this in a sum, right? Let me comment this, I don't want to delete. It works. It's not that fast, again, but maybe it will be faster than before. I hope. It is faster. I mean, same result. Okay, so this was day 6. Let's commit that. What did I add here? Oh, the graph from the other day. No, we don't need the graph file. We don't need these two. We don't need the pet graph, at least not today. We need to, oh, we didn't add the day 5, but it's okay. So I'll see 2024 day 6. Let's push day 6 and let's start on day 7, which is today. We scaffold day 7. We get the code, we get the example from the calendar. So let's go to the calendar on day 7. Oh, that was a lot. What time is it? It's 45, okay. So, bridge repair. The historians take me to a familiar rope bridge over a river. He isn't on this side of the bridge. Can it be on the, might it be on the other side? We don't know. When we cross the bridge, you notice a group of engineers trying to repair it. You won't be able to cross until it's fixed. You ask how long it will take. They tell you that it needs final calibration, but some elephants were playing nearby and stole all the operators from the calibration. Okay. They could finish the calibration if someone could determine which test values Should we read all the text? Oh, it's fine. This is the example. And each line represents an equation. So each line is an equation. The value on the left appears before the column on each line. It is irrelevant when the remaining numbers can be combined with the operator. Okay, so we need to solve... oh, it's like one of the tests you see on Facebook or Twitter. You need to fill the gaps in here with the operators. Well, I don't know how to do that right now. They are always evaluated left to right, not according to the precedence rules of the operators. And furthermore, the numbers cannot be rearranged. Okay, so we need to try with just the add and multiply. Okay, this gives me an idea. Only 3 of the above equation can be made through by inserting operators. So the first one, the second one, and 292, and the last one. Okay, so we need to get the calibration result. Okay, we need to get the sum of the values on the left just for the equations, which can be solved by putting plus and multiplication inside the equation. Okay, what is their total? Okay, let's start by parsing this input. Now let's start. Yeah, I think I have something in mind. Let's see if it works. I think we can do. But when you have this kind of problem, you should usually use like it's a permutation search. So we could either try to all the permutations of plus and multiplication inside the equation, but I think it gets pretty big in the inputs. So it's not that small. Also, the numbers are not so small. So this is not a U32. I think it's a U64 because it's over the 4 billions. And I mean, they are not too much, but it's 1, 2, 3, 4, 5, 6, 7, 2 to the 7 tries. So it's at least 100 tries for each line. It's not that much, but I think we can do it better with search algorithm, like with recursion. So I can try with the first one, put a plus or a multiplication inside and go to the second one. The thing about addition and multiplication is that they can just go up and not down. So if we get over the number on the left, then the equation is wrong for sure, and we need to get back. So this can be a depth first search with a bound. So we have a bound, which is the number of the left on the left. So let's try to write the search. No, we can try to test first that we can check these equations. So we can be sure. Let's use a rest test. So we can have a function test. We need to check the equation. So we have a given result, which is, let's use U64 this time. We have a U64. We have an equation, which is a vector of other U64 numbers, and we need to see if it's valid. So it's a Boolean. We assert that valid is valid of the equation given the result equation. Now we need to write the is valid, and we need to write our test cases. So we need to give it parameters. This is case. This is in the case. This is in the case. Now let's write the ones on the examples like this. We can do something like case of the result, the numbers, and most of them are not valid. So we do like this. We know that the first the second and the last are valid. So we can do that. And here we need to put a vector. Wait, a vector of u64. So we can do like this. And here now we just need to put the commas. Way too long. Can I just do... No, let's do it by hand. I don't want to mess with the code. Just some commas. Not here. Here. Not working because I didn't import RS test thing. Okay, now it works. We need the space here and we need the is valid. So function is valid of result, which is a new 64, and the equation, which is made of operands and is a vector of u64. We return a boolean. Now, how can we create the recursion here? I think I need more than this, so we need at least an intermediate result, which is the current. We basically accumulate from the left. So we start from this number, like 6 plus 8 means we get a result of 14, and we need to check against the result. Then we go on by 6, so 6 plus 8 by 6. So if we go, given that we don't have a predecessor of operators, we can just go from the left and accumulate. So we need an accumulator, and this can be done in our is valid. We need an accumulator, which is another u64, and an index to get the current, the next. We could use a slice, but I don't know how to use them. I mean, we can try to see, but let's start with the index and then we go on with the index is a usize. Now I like to use this to do clean methods, so this is an helper. And we call the helper from the isValid method. So we return isValid over result equation. Now the accumulator can already be the first number, so we can just give it equation of 0, and the index is the next one, so it's 1, and we just return a boolean. Now why? Oh, it's moved, so let's... Can we clone the number? I hope so. Wait. Can I clone the number? Yes, I can. This must return a boolean, so why is it not working? Expect a semicolon. No. Okay. Again, equation is borrowed. Let's get a reference so that we don't have issues. This should be copied, and now let's write the helper. So, how does it work? If we are at the end of the chain, we need to check for sure against the result. So if the index is equation len, we've gone over the len, and the accumulator is equal to the result, then we return true. Right? Otherwise, if the index is less and the accumulator is over the result, this is what I said before, we return false for sure, because we cannot go on anymore. Then the number will surely go up, and we don't want it. Otherwise, we check for the two operation. So we have the addition result, which is in which we call the helper again. Let me do that. We call the helper with the same result, the same equation, accumulator plus current number, so equation of idx, and no, it's the accumulator plus, okay, and idx plus 1. Same thing for the multiply result. So the multiply result here needs a multiply symbol, and we return add result or multiply result. If one of these two, basically we branch here. If any one of the branches is fine, then it needs we went to the end and we came back and it's all true. Otherwise it is false. If both branches are false, then it's not working. Now this is valid. Doesn't work because I need to pass a reference expected for arguments, but is valid as, oh, okay. Don't need this thing anymore. And is valid helper. Okay, let's test it. Let's test binary 7. Oh, it failed. Okay. Yeah, we're not getting the less than. So if it's well, we can just return this. If we are at the end, either it is equal or not, and it returns false. So now it works. Okay. So let's solve. No, we cannot solve. I need to parse the inputs. So let's put the. So we have the example. We need to return 3749 here. We need to do this thing. Now we need to parse the inputs. So for each line, let's do it in a single iteration. So if we iterate over the lines and we map and filter together a line, now this will be a long method, then we can sum the numbers and return them as u32 sum, like this. Now here, either we return an option of u32 if the line is valid or not. Let's get the result and equation from the line. So it's line split, I think split once. And here we split on the colon space. It's not a character, it's a string. Let's do it like this. Then we need to split again we need to parse the result. So the result is result parse, like a u32, unwrap, and the equation is the equation split by white space or by space, like this. And then for each one of them we have a string which needs to be parsed. First u32, again unwrap, and we collect this into an equation. Please. Finally, after collecting this, we return if is valid. Result and equation. We return sum of the result. Otherwise, we return none. And this is not valid, so we don't need this now. This is mismatch closing delimiter. Did something wrong here? I didn't, yeah, need to do like this. Color? Yes. Oh, we need to unwrap here. We are sure about the. We're sure about that. The result is a okay U64 actually for every number because we're not sure about the size right here. The sum must return a U64 because they are big. There's U64. Sum doesn't work. Cannot infer. Why? Filter map. It's returning an option of result, which might be a. Okay, let's go on the usage and yeah, should work. Why shouldn't it work? Let's give it a type just to be sure, but I don't think it should have issues. I mean, I don't know why it's asking for a type, but let's see. Now, cargo test again, the binary. It works on the first try. Maybe we are lucky with solving. So let's solve 07. But this is a big number. I hope it's the right one. It is the right one. Okay. So part 2. The engineers seem concerned. The total calibration result is nowhere close to safety tolerance. You spot your mistake. Some hidden elephants are holding a third type. Okay, so we have a third type of operator. The concatenation combines the digits from the left and right inputs into a single number. Okay, all operators are still evaluated. So this is a new operator which is evaluated from left to right. Now, apart from the 3 equations that could be made true using only addition and multiplication, the above example has 3 more equations that can be made true by inserting operators. Okay, so we need to create new numbers by concatenating 2 numbers together. Wow, this is big. Okay, it's I don't think it's a multiplication. It's kind of like a multiplication, so it still increases the size of the number. So I think the algorithm stays the same. We can try. So adding up all the 6 test values produces a new total calibration result. Using your new knowledge, determine which is which. Okay, so we just need to add a new operator, which we don't know how to write, but it's okay. Okay, let's see. So this is similar. We just need to concatenate 2. Now, let's copy this code just to be sure. With concat and with concat, we can directly try with part 2. So we just need sum of 11387. We copy the code from part 1 and then we will just refactor this. Now, this is the same, but we are using is valid with concat. Let's add concatenation, which is a third branch here. So this is the first, this is the multiplication, we add the concat result. Let's make it the same as multiplication for now and make the test fail, then we will write the concatenation operation. So this is not working because part 2 is returning a U32. So let's return a U64. It fails. Okay. Let's write a couple of tests for the concatenation operator because I don't know how to do that. I mean, I don't know how to. How do we concatenate numbers? We just we need to find how many digits it has, multiply it. So like if we have, let's write it. So concatenate two numbers. The first A is a U64. The second B is a U64. We could try to divide the number every time. We can just call, I think, a log10 function. Yeah. So if we have like 100, we have 111. We want to concatenate with 2. We need to have a logarithm of 111, which returns, I think, no, a logarithm of 222. This is all in comments, by the way. I'm not writing Rust code right now. I'm just fiddling with code. So we get 10 to the second. Then we need to do 111 by 10 to the second. 2. Right? Well, this should be 3 because we need to. I mean, let's try. I don't know how to do that, but log 10 of this number. I hope that, yeah, 2.34, so it's rounded up to 3. Now let's see if in Rust we have a way. So get number of digits. I mean, we already have the digits. It's just that this is a number, and we have strings in the input. We could use the strings. Get the number of digits. Length of an integer from string radix. Okay. No, string from radix. Okay. Repeat with, take a while. Log 10. Don't they have a log 10 already implemented? Because log 2 is easy. Otherwise, we could try to do it with log 2. Like, don't we have to, like the log 2? Local of log 2. We have log 2 plus ceil. Okay, so like we could try to do. Oh, let's test the concat because I don't know how to test it. I want to test this. I want to test concatenation. I want to assert that concat of 11 and 22 is 11, 22. Okay. How can I do that? Concat returns a U64. Now, how can I do that? Let's write the failing test. So we return 0. Test concat fails. I return. Do we have bit shift operators in Rust? No. Bitwise operators. Okay. Binary, unary. Okay, so we can shift right or left. So we need to, let's call this left and right, otherwise I will get mad. Now we need to have the logarithm too. So log 2. Do we have a log 2 in Rust? I hope so. So if we do right log2. Seal. And we return the left. No. Yes, the left shifted by the number of logarithm. It doesn't work because we don't have a log2. There is a method, ilog2. Leading zeros. No. U64. ilog2. Base 2 logarithm of the number rounded down. Now, I don't want it rounded down, so do you have like ilog2? Rounded down. Don't like this down. So how can I log? Is there a log without the I? Wait, what did I do? Wait. Don't know how to switch workspaces anymore. Wait. I'm back. Just didn't know how to switch workspaces. So how does it work with the leading workspace, with the leading zeros? Number of leading zeros in the binary representation. Depending on what you're doing, you might be interested in the ilog2, which returns a consistent number even if the type widens. Leading zeros. So leading zeros of 0 is, this returns a size, but I don't want this. I'd like the ilog2. But I don't know if I want the round down. That's the thing I don't like. We could try with the leading zeros, like this response. Okay, this is too much. Maybe we want this. Thing is, I want to call it with a. Let's try to do it like this. So let digits, not bits, actually. This is. I want it as. To integer to. Can I just round it? Not round it, but count it as U64 to bit. No. How is it? No, to integer. No, I don't like this again. I just want to add this to numbers. It should be easy. Get number of digits. Not the digits, number of bits. Number bits. Bitwise cheat sheet. Okay, this is. No, I don't want the size. Get number of bits of a number in Rust. This is okay. Shift. This is not useful. Number of bits. Number of bits necessary to represent this number. Is it that difficult? Oh, this is not the same thing, I think. Oh, let's see. Bitlen. No, this is a request actually. 2016. ilog2. Let's try with ilog2. And see if this works. I don't think it will. This is not the same. This is definitely not the same. So let's do ilog10 and left power of right plus right. No, again, it doesn't work. 33, that's not right. I mean, log 10 of I want more. This is 22. We're talking about 2 digits. So I should raise 11, and not 11, it's, wait, by 10 to the power of times 64 power of the right. So 22 is, I think, 1 and something plus 1. So this is 2. So it's okay. Let's try. Let's just try. Okay, now the test passes. This is 1 test, and it's okay. Let's try with other numbers because I'm not entirely sure. So let's say we have wait. Let's say we have 100, like a number which is power of 10. We have 34, 32, and 100 with 32. 100. It's okay, it's working now. Instead, this concat works. Let's run the concat method. So in the isValid1, we have the tree operation, and this is concat of accumulators with the number on the right. This is way higher than the multiplication. So let's, okay, it's failing. Why? Nice. Does it concatenate? Yeah, it should concatenate everything. Okay, so why is it not working? We're getting the same number as before, I think. Are we calling the right method? isValid with concat? Yes. Let's see. Let's go back to the problem. Now here, 156 can be made true. Okay. Maybe we can write a test like the other one and see which one fails. So we write the test for every case. Now we test part 2. So 190 works, 156 should work. 7 to 90 should work in some way, and 192 should work with the is valid with concat. Let's write some tests. Okay, it's not working right. Test equation check with concat. Otherwise it won't work. So we have 2 tests failed. With concat phase 1, 2, 3, 4, 5, 72, 90. Why? Here it says it should work because 6 by 8 concatenate with 6 by 15. So it's 6 by 8. Let's bring out calculator. 6 by 8, which is 48, plus 6, so 48, 6 by 15. 7 to 90. Now, something is not working in our concatenation function. So let's try to concatenate 48 and 6 in our test. 4, 8, 6. 4, 8, and 6. And in fact, it's not failing. Okay, so the concatenation is working. Okay. So what is not working? Let's try to print our the is valid concat. So concat result is equation of idx, and this is okay. I mean, maybe it's this concat which is not working. Let's try to debug the accumulator and the index. Actually, let's try to print, otherwise I will get mad. So this is the accumulator, this is the accumulator, this is the edx. We should get 486 at some point. We should get, not in part 2 test, but in the check with concat case 5. 6, 1. Case 5. 6. Case 5 is 6, 8. It's 6, 8. Why is it not printing? Okay, this is when it ends. This is when it's more than the result. Let's actually not write the... This is the index, this is the accumulator. Let's write the accumulator. We should write the equation of ADX. Here, println of the accumulator and the equation. So the accumulator equation of edx. Let's print stuff. Here we are in the. Let's remove the part2 test because I'm using the wrong valid. I mean, let's remove this test for now. I just need one test failing. Perfect. It's just printing 6, 8, which is the first two. 6, 8, and nothing else. It panicked. Okay, why is it panicking? Because it's coming back. What is the result here? Wait, is valid helper with concat? I also need the result. Result. Accumulator and n. Why is it failing like that? 6 and 8. It didn't print anything else, so let's try to debug. Maybe with the debug it will work better. No, it didn't. It fails right there. It returns right away. Oh, it's using. Oh, fuck. Okay, I see. I'm not using the right helper. Stopping there at the first iteration. Now it works. Okay. And let's try with part 2 again. Let's test again. It works. Let's solve part 2. Hope this work. It's way higher than before. So it should. Right answer. Okay. So we did day 7. Now let's fix this code. Let's fix this code. So first we can rewrite this is valid with the operations. Like first thing we can write the we can first we can this is the same code. We can just refactor it and use a different function. So the function is valid with concat or is valid. So we can write like a function solve, which takes a string and returns an option of view64. It also takes a function which we will call. So first we extract this. So solve for input with a function which is valid with concat. Hope this is the right way. And the other thing is solve with is valid. So with is valid. This is the first we can try. So is valid. The function is valid is a method. It's an fn once and fn implements a function which gets a u64 and a vector of u64. And reference to a vector of u64 and returns a boolean, right? This is the valid fn. Does this work? It does. So we are fine. Let's test. It works. And this is the first thing we can do. This is the solve method. No, the if is okay. We can also create isValid function. We can actually rewrite the isValid helper function by adding the set of operators we can use. So we can write the operators here. An operator. Now we can make it parameter. Yeah, we can create parameters. So for example, the isValid takes also a set of operators. No, the isValid helper takes a set of operators. Operators is a vector of operators. Now, how can I write an alias? Otherwise, no, it's fine. The operator is a function. The operator is a function which takes a U64, another U64, and returns a U64, right? This is the function, the vector of functions which we need. Now, operators is passed here. It's just passed right away. Operators. And don't need this, we can do operators, iterate over that, map with the result. So the operation is this, then we return isValid helper of operator of ACK and equation of IDX. And then, no, we can filter. We can call and return any of these two. We like it? The operator is working. This is a vector of operators. Now the isValid, we can write it at operators equals to a vector of first a lambda. So we take A and B and return A plus B. Then we have by multiplication, and we have the concatenation. Concat of A, B. This is a vector of operators. We can pass it here. No, this is the isValid. So we just need these two. The isValid with concat, otherwise is, the other end is this. So we return isValid helper with three operators. A by B, A plus B, and concat of A and B. And isValid helper with the operators we have. This will go badly. It works again. This is even better. Let's remove a parenthesis here. And can we make it better? No, I don't think so. So if we solve it, again, we get the same numbers as before. The test works, and we are fine with day 7. Let's save and commit the day 7. Day 7. And so this was day 7. and see you. I don't know if we will see tomorrow for day 8 or on Monday for day 8 and 9. So see you.